Hello, hello, hello everyone. Welcome to our lectures. And today we are very happy to invite the Professor Mike Rosulek to give a series talk on secure multi-party computation and Rosulek circuit. Today's lecture is the third lecture, and the topic is oblivious transfer and extension. Mike is an associate professor in the School of Electrical Engineering and Computer Science at Oregon State University. He received his PhD in 2009 from the University of Illinois. He's the author of over 5 peer-reviewed articles on various topics within cryptography. His main research focus is on protocols for secure multi-party computations. His work has been recognized with a prestigious Career Award from the National Science Foundation, as well as research awards from Google, Facebook, and VESA. The organizers are Shanghai Qizhi Institute and Shanghai K Laboratory of Privacy Preserving Computation. And next, I will pass the microphone to Mike. Hi, Mike.
Hello, can everyone hear me?
Yeah.
But thank you for the introduction and thanks for having me back. I'm glad to be back. Today, as the organizers mentioned, I'll be talking about oblivious transfer. And if you recall, oblivious transfer is a special case of secure computation. There's a sender and a receiver. The sender has 2 messages. The receiver has a bit that it uses to choose which of the messages to learn. So it learns one of the 2 values of its choice, but it doesn't learn anything about the other value. The sender doesn't learn anything about this choice bit C. So that's oblivious transfer. We use this in Yau's garbled circuit protocol to deliver the wire labels to the evaluator. So for the input wires, we need to let the evaluator learn one of the 2 possible wire labels on each input wire, and we can use oblivious transfer to do this. So one oblivious transfer instance for each input wire in the circuit. So this is something that's necessary for Yau's protocol, but it's also used in many other MPC protocols. I think we'll see some examples of this in my next and final lecture about private set intersection. But you have seen oblivious transfer in Yau's protocol, and it's a very important step. It's very expensive. So if you can remember 2 weeks ago when we talked about Yau's protocol, when you garble a circuit, all of those operations are symmetric key operations, right? So yeah, you would encrypt each gate of the circuit in a special way, but you would encrypt it with symmetric key encryption, and that's very fast. But oblivious transfer is not so cheap. It's expensive. It uses public key crypto operations. For example, there's oblivious transfer protocols based on Diffie-Hellman. It turns out that it's impossible to build oblivious transfer just using symmetric key cryptography. There's a way to formalize this in a very famous paper by Impagliazzo and Rudich. If you're interested, it's a very important result, but that's not the focus here today. Our focus is oblivious transfer is expensive. It's possible that oblivious transfer can be the most expensive part of a secure computation protocol. So I want to talk today about different approaches for making oblivious transfer cheaper. So there's 2 main approaches. The first one is very simple. There's a nice way to compute oblivious transfers offline, pre-computation in an offline phase. So you can do all the hard work in an early phase before you know your inputs. So before Alice and Bob have chosen M0, M1, and C, before they know those values, they can do most of the hard work, maybe during a time where computation is cheaper. And then later they can kind of use what they computed to perform an oblivious transfer that's very cheap in the online phase. So that's a very simple trick. It's a nice trick to know about though. So I'll talk about that first, and then I will talk about OT extension. So OT extension is this idea that if you just have a small number of real oblivious transfers, like 128 of them, then there's something you can do by only using symmetric key cryptography to get an unlimited number of oblivious transfers. So basically, once you have 128 oblivious transfers, that's all you need. And then everything else you can do with symmetric key operations. That's a little bit more complicated, and I have much more to say about OT extension, but that's what we will talk about today. So first, I'll talk about this pre-computation idea. So the way I describe oblivious transfer usually is in this picture. So Alice has two messages, M0 and M1, that she chooses. Bob has a bit C that he chooses, and he learns MC. You can think of a slightly different version of oblivious transfer where the parties don't get to choose these values, M0, M1, and C. The protocol chooses it for them, and it chooses them to be just random values. So you run the protocol, and as a result of the protocol, Alice learns M0, M1, Bob learns C and MC, but they didn't get to choose. They didn't get to choose these values. So that variant is called random OT. Yeah, so random OT is this randomized functionality with no inputs, basically. And there's a nice trick by Donald Beaver from 1991. Actually, a lot of the interesting results from today are ideas from Donald Beaver. He was like the master of oblivious transfer back in the 90s. So he showed in the 90s that if you perform an instance of random OT, then there is an easy way to convert that random OT instance into a standard OT instance. In other words, Alice and Bob perform random OT, so they didn't choose these M values or the C value. Then sometime later, they decide on inputs to a standard OT, and they can somehow very cheaply convert this information that they got from the random OT. They can convert it into an oblivious transfer for these chosen inputs. So what this means is that if Alice and Bob know that sometime in the future they plan to do some secure computation, and they know that oblivious transfers are involved, they can prepare by running lots of random OTs. I'll call that an offline pre-processing phase. You don't need any inputs to do a random OT. You just decide to run a random OT, and then you get outputs. Then sometime later, they actually run the secure protocol, secure computation protocol, maybe Yao's protocol. And Yao's protocol says run oblivious transfer with these particular inputs. So during that time, they perform this cheap conversion where they convert the random OTs into standard OTs using this Beaver trick. Okay, so that's what I will describe. So here's the setting again. So the two parties have performed a random OT. So I'll put a $ in the exponent to mean that these were values that Alice and Bob didn't choose. It's just whatever random result of this OT protocol. And the arrows also indicate that they didn't choose these things as inputs to the protocol, they came as outputs from the protocol. Okay, so Alice and Bob have this data that's correlated in a special way. You see that this M value is correlated to these two M values in a particular way. Okay, now later, they decide on their OT inputs. So Alice decides on M0, M1, Bob decides on C, and they want to make sure that Bob can learn MC without learning the other M value and without Alice learning C. Okay, so how can they do this? Well, one idea is that Alice could use these random values. So I'll call these values M0 random and M1 random. She can use them as one-time pads to mask the values that she really wants to send, right? So she could, so think of these as one-time pad ciphertexts. So if this X0 is a one-time pad ciphertext, it means that if Bob knows M0 random, then he can decrypt this first ciphertext and he can learn this chosen M0. That's what we want to happen. Okay, so that's kind of the idea, but let's see if this actually works. In the offline phase, Bob picked up this choice bit C random, and then later on, he decides on a chosen input C for the oblivious transfer. And if these happen to be the same, like C and C random, if they happen to be the same, then things work out just fine here. So Bob knows this MC random value. And so he can, yeah, it's basically, yeah, it works out. It's maybe not too exciting for me to read the equation, but it works out that Bob wants to learn MC, and he already has the one-time pad that was used to mask MC. He doesn't know the opposite mask, so he gets no information about the other chosen M. So this is fine, but sometimes Bob doesn't get lucky. So he wants to run oblivious transfer with a particular choice bit C, but in the offline phase, he was handed the opposite value for C random. So if you wanted things to work in this case, then Alice would need to switch which mask she uses, right? So imagine C is 0, but C rand is 1. So Bob knows M1 rand, and he wants to learn M0. So you would need to encrypt M0 using M1 rand as the key, right? And that's what would be needed if you want this to work. So sometimes Alice needs to switch the one-time pad keys that she's using. How does she know when to switch? Well, Bob can just tell her. So Bob can actually say whether C equals C random. Since C random is random, then this leaks no information. And actually, what does it mean to reveal whether these two values are equal? It's the same thing as revealing their XOR. Their XOR is 0 if the things are equal, and it's 1 if the bits are opposite. So let's have Bob, he reveals whether C equals C random. Since C random was chosen uniformly at random, this message does not leak anything about his actual choice bit C. I think you can see that that's true here. And then based on this bit that Alice gets, that's how she chooses whether to swap the one-time pad masks. So you can work through this and you can verify that it works. I have it on the slide here. I think this is going to be recorded. So this is a slide that it's not too difficult, but you just need to stare at it for a while and check that everything works out. But the way I like to think about it is Bob tells Alice whether she needs to kind of swap whether to swap 0 and 1. And then she just uses one-time pads to mask the messages that she wants to send. So this is a very simple trick. And it turns out that many tricks, many primitives in secure computation have this property where you can compute this function on random inputs in an offline phase. And then later in the online phase, you can convert them into a chosen input instance. So I just want to draw your attention to the fact that in the offline phase, it's maybe expensive because it involves running an oblivious transfer. But in the online phase, the only thing that happens is some XOR operations. So those are very fast. So in situations where you can generate these, you can generate them at night when electricity is cheap, something like that. And then later on, we want the computation to be fast. You consume these pre-processed oblivious transfers in a very cheap way. And I should also point out that you can only use this random oblivious transfer to generate one instance of normal oblivious transfer with chosen inputs. And the reason you can only use it once is because you use these outputs as one-time pads. Actually, all of these are one-time pads. So Alice uses these as one-time pads. Bob uses this kind of as a one-time pad to mask his true choice bit. So it's just a one-to-one conversion from random OTs into chosen inputs, chosen input OTs. Okay, that was pretty quick because that's a nice simple trick. This Beaver, I call it OT derandomization. So next, I'm just going to talk about OT extension for the rest of our time here. And I'll split it into 3 parts. So I'll just introduce this idea of OT extension and show you kind of the classical ways to achieve it. Then I'll talk about malicious security, which has a nice trick. And then I'll talk about some generalizations. Okay. So I want to motivate OT extension using public key encryption as an analogy. So like I said, oblivious transfer is expensive, and there's good reason to believe that it has to be expensive. It has to be more expensive than symmetric key cryptography. And it's the exact same reason why we think public key encryption has to be inherently expensive. So actually, I'm citing the same paper here. The paper actually showed that if you only have symmetric key cryptography, you can't do key agreement. But it turns out that if you had oblivious transfer, you could do key agreement. And if you had public key encryption, you can do key agreement. So that implies that if you just have symmetric key cryptography, you can't do either of these 2 things. They have to be expensive. But we use public key encryption all the time, even though it's much more expensive than symmetric key crypto. And the reason we can use it all the time in practice is that we don't encrypt everything with public key encryption. We use public key encryption to encrypt a short secret. This is hybrid encryption or key encapsulation, which you've probably seen. We use public key encryption, right? You wouldn't use RSA to encrypt a gigabyte of data. You would use RSA to encrypt a short key, like an AES key, and then you use AES to encrypt the gigabyte of data, right? So as long as you can do public key encryption of something that's maybe 128 bits long, then you can do everything. You can encrypt long messages with public key encryption, but the cost of the expensive stuff is limited to just encrypting 128 bits. So this is very well known. This is why we can use public key encryption. So OT extension is like asking the question, can we do something like hybrid encryption for oblivious transfer? So wouldn't it be nice if, suppose I really wanted 1 million instances of oblivious transfer, I could just run an oblivious transfer protocol 1 million times. Wouldn't it be nicer though if I could only run 128 instances of oblivious transfer, and then using lots of cheap symmetric key techniques, I somehow obtain 1 million instances of OT. right? In the same way that I could get public key encryption of gigabytes of data using hybrid encryption. So that's what oblivious transfer extension gives us. So this was another really incredible idea by Donald Beaver, this time in '96. So when I first heard about this, I thought this was probably not possible. I didn't quite believe that you could somehow use a small number of oblivious transfers to get a large number of oblivious transfers for at a cheap cost. But this result of Beaver showed that it's possible. And so I just want to convince you first that it's possible. Okay, so this slide is going to be a very theoretical feasibility result. It's not a practical OT extension protocol. But if you think back about why we need oblivious transfers for Yao's protocol, we need an instance of oblivious transfer for every input wire in the circuit. If we are evaluating a circuit, we need an oblivious transfer on every input wire. So OT is proportional to the input of the input length of the function. So Beaver had this idea. He said, what if you used Yao's protocol to compute the following circuit? So the circuit takes as input a contribution from Alice and Bob that's just 128 bits. And you could think of those as secret shares of a pseudo-random generator seed. So the circuit takes those two shares, it reassembles them, it expands that seed into a really long pseudo-random sequence. It splits that sequence up into a bunch of strings. It gives all of the strings as output to Alice. And then it also samples a random string of choice bits. And it, right, so if the first bit of R is 0, then it will give M1 0 to Bob, right? So it gives half of, it chooses a random half of these strings to give to Bob, and it tells him which of the two strings he's receiving. So, right, so this R value is telling him whether he received the 0 message or the 1 message for each of these n different instances. So this thing that I drew in the box is just random OT. It's n instances of random OT. Right, for each index I, you can see that Alice learns M0, M1. Bob learns one of those two, and he learns which one he learned. And that happens n times. Okay, so write out this circuit. This circuit has like a pseudo-random generator inside of it. Use Yao's protocol to securely evaluate this circuit. Now, Yao's protocol only uses a number of OTs that is proportional to the input length. Well, here the length of the inputs is just lambda bits, like 128 bits. So you securely computed these values, and you only needed 128 bits of, you only needed 128 instances of OT. But the output that you got was n different instances of OT, of random OT, pseudo-random OT, I suppose, but close enough to random. And n can be much larger than 128. So even if this n is 1,000,000, then this method generates 1,000,000 instances of random OT using only 128 instances of actual OT. Yeah, this is such a simple idea, but I found it surprising, and the explanation is very simple. So based on everything I showed you in the last lectures, it's easy to understand how this works. And it's easy to understand that it only uses a small number of OTs, but it generates a large number of OTs. Okay, that's kind of cool. The problem is that this is not really a practical way to generate lots of OTs, because you have to use Yao's protocol to evaluate a Boolean circuit, and that Boolean circuit includes the description of a pseudorandom generator, right? So that's kind of a big, complicated circuit, and you're doing symmetric key operations for every gate in the circuit, so that can be pretty slow. Calls a pseudorandom generator like a million times. That's a huge circuit with lots of gates, and every gate requires some effort. It only requires symmetric key operations, but it requires a lot of them. So this is not very practical, but it should convince you that this is possible. Okay, so now that we know it's possible, we can look to find better ways of doing it. So I think this next paper that I'll talk about, we call it IKNP. It's the names of the authors, IKNP. This paper from 2003 is maybe the most, I think it's the most important paper for two-party secure computation that I can think of, at least since like Yao's original, yeah, maybe Yao's protocol is #1, and this is probably #2. So this is, yeah, one of my favorite papers. So I'll try to explain this really nice way of doing OT extension. And I think before we start, I want to make a distinction between these. We call these. So I'm saying you use 128 instances of OT to generate n instances of OT. So I'll call the 128 instances base OTs. So you actually run n lambda base OTs, and you use them to generate n extended OTs. Okay, so I think it'll be helpful to distinguish between base OTs and extended OTs. All right, so here's how the IKNP protocol works. Yeah, these slides are a little bit more complicated than most of the other slides I've shown you. This protocol has to do with lots of matrices, and you look at the matrices across the columns sometimes and across the rows at other times, and it gets to be a little confusing. And I tried to make it make sense, but the only way to make it make sense is to have lots of matrices on the page at the same time. So I apologize for that. So here's the setting. Alice and Bob want to do maybe 1 million instances of OT. So in each of those instances, Bob has a choice bit. So in the first bit, he wants to learn message 1, and in the second OT, he wants to learn message 0. So I'll call those values R. Those are his choice bits in all the instances of OT. So this is a column that's like, all of these matrices are going to be tall and skinny. So this is, right now it's just a vector with 1 million entries. He's going to extend all of these choice bits into a matrix, just duplicate this column many times. So now he has a bunch of rows that are all 1s or all 0s in each row. And then he's going to secret share this matrix. So here's one matrix, and then he secret shares it into 2 matrices, and the result looks like this. So I tried to highlight, I highlighted here in orange places where this top matrix is complementary to the bottom matrix. And that happens whenever R is 1. So whenever this R value is 1, the 2 rows are complements of each other. And whenever the R is 0, these 2 rows are equal to each other because they're secret shares of 0. Okay, so when they're opposite each other, I made them orange. Okay, the width of this matrix is maybe 128, and the height is 1 million. Okay, so there's secret shares of this special matrix, and now we're going to run these base OTs. So Alice is going to choose a random string that has it's only part of the IKNP protocol. It's not part of her 1 million OT inputs. It's just a random string that causes this all to work. Now they're going to run base oblivious transfers. They're actually going to run them in the opposite direction that you might think. So in the end, I want Bob to be the OT receiver. So this is his choice bit for each of the million OTs. But in the base OTs, Bob behaves like the sender. So for every column in this matrix, they're going to run an oblivious transfer. So in this first oblivious transfer, Bob's two inputs are these two rows that I highlighted, like these two orange rows. Those are the two possibilities. Alice chooses which one to pick up according to this bit of S. So here her bit of S was 0, so she picked up this row, and she didn't learn anything about this row. Sorry. And they do that for each row. So here, Alice had a choice bit of 1, so she picked up this column. And I kept the orange bits around because the orange bits are important. Of course, Alice doesn't see that this is an orange 0. She just sees that it's a 0. Okay, so this is how things work. For every column of this matrix, they perform oblivious transfer, and Alice picks up one or the other. Okay, now let's compare what Alice knows and what Bob knows. Whenever let's look at this second row of these matrices. Bob had a choice bit of 0, and that means that this second row here and this second row here are the same. So that means it doesn't matter what S is. Whatever Alice sees here is going to be the same as what Bob has. Right? So that's all these rows where Bob's choice was 0. When Bob's choice is 0, it means that S has no effect. You'll always pick up the same thing that Bob has in these rows. So those are the gray rows. That's what happens. So the Alice row equals the Bob row. Whenever Bob has a 1 here, then those two secret shares were complements of each other. So whenever Bob has a 1 here, and whenever Alice has a 1 here, she picks up the opposite bit that Bob has, right? So you can see these orange, that's why I left the orange ones in here. So orange is all the places where Alice's matrix is different than Bob's matrix. And these orange places, they only happen in rows where Bob has a 1 in this position, and they only happen in columns where S has a 1 also, right? Because this matrix I have here is what you would see when you had when Alice chose a 0 here. And another way of saying that is that whenever you're in a row where Bob has a 1, then the thing that Alice sees is Bob's row XORed with S, right? So just look at this first row. Take this, XOR it with S, and you would get exactly the value here. This is the magic of IKNP, this relationship between Alice's items and Bob's items. And I think it took me a long time to figure out why this works. I have to draw it out in many different ways to understand it. But this is the main idea. So I've just captured this observation. Whenever, so they do oblivious transfers. They do the base oblivious transfers by the columns. And then we start looking at the rows after that. So Alice learns a bunch of rows. I'll call the rows of her matrix Qi. And Bob also has a matrix that I call Ti. its rows are ti. And this is the property that they satisfy. If Bob's choice bit is 0, then qi equals ti. And if Bob's choice bit is 1, qi is ti XOR s. Okay. Yeah, so this picture, actually, every time I'm thinking about I, K, and P, or I'm talking about it with my students, I draw this equation on the board every single time, because otherwise, this is the only way I know how to understand how I, K, and P works. Actually, I usually look it up in a paper and then copy it onto my board. Okay, so Alice and Bob have these Q's and these T's, and they're correlated in this way. So let's imagine that Alice also knows this S. S was a value that she chose. So she can compute both Qi and Qi plus S. So suppose she does that. Now I'm going to simplify these Q values according to this expression. Okay. So here in this first case, maybe if Bob had R1 equals 0, then we're in the top case, and Qi equals Ti. So these two are equal. Sorry, these two are equal, and then the plus S is over here. But if this R bit was a 1, then T2 equals Q2 XOR S. And then it looks like this from Bob's perspective. And what I want you to see in this picture is in every row, Alice can compute 2 different values, and Bob knows one of those 2 values. And which one does he know? Well, he knows exactly the one that corresponds to this bit that he chose. That's his choice bit. This is starting to look like many instances of oblivious transfer. Like if this matrix was 1,000,000 rows tall, then this is starting to look like 1,000,000 instances of oblivious transfer, right? Alice knows 2 items. Bob chose which of the 2 things he wants to learn. It's not quite oblivious transfer because these values are not random. It's true that Bob knows one of the 2 values, but there's correlations to the values he doesn't know. So we actually want this to be like a random OT where like suppose Bob knows T1, then this other value should look uniformly random to him. But actually all these values that he doesn't learn, they don't look uniformly random. They look correlated because they are correlated with the same S. So in order to fix that, all you have to do is put these values through a random oracle. So each one of these values, like T2 XOR S, that value individually has high entropy, and Bob cannot guess that value, but it's correlated to other values. But if you put it through a random oracle, that sort of breaks all the correlations. So this was a value that Bob couldn't guess, and that means that the output of the random oracle is independently random. Okay, so both Alice and Bob can hash these 2, hash the values that they learned, and now we really do have random OT. Like this is the IKNP protocol. So I'll just rename the values here, and they satisfy this property. So in every row, Alice can compute 2 values. Bob can compute 1 value. He learns one of them, and the other one looks random to him, independently random, independent of everything. So that's the magic of IKNP. You can check this. You can check that this makes sense to you in the random oracle model. This is like a kind of a pseudo-random function, h of x plus s, where s is the key. That's like a pseudo-random function in the random oracle model. Okay, so this is the IKNP protocol. I think it's hard to it's hard to master all of the mechanics here. So I think what you should try to focus on is this big picture. So we have these very tall, skinny matrices. There are lambda columns. Always think of lambda equals 128. There's many rows. Always think of a million rows. They perform base OTs for every column of these matrices, right? So for every column, Bob has two, secret shares of something, and Alice chooses which one to learn. So there's only 128 OTs. Then they take the matrices that they learned, and now they look at them according to the rows. And within each row, Alice does some XOR and then computes some random oracle hash, and Bob computes a hash of his thing. But the thing that scales with the number 1 million is the evaluations of the hash. And so for each row of these matrices, we get an instance of random OT. Okay. Yeah, the more I learn about this IKNP protocol, the more I'm really amazed. It's very nice. If you try to improve on it, you usually fail because it's just kind of perfect. Okay. So far in these lectures, I've only talked about semi-honest security. I haven't talked about malicious. And it's actually true that this IKNP protocol is not secure against malicious adversaries. So I want to demonstrate why that's true. But there's a simple trick from a few years ago that teaches us how to make this secure against malicious adversaries. So I'll talk about that next. Okay. And the good thing is that when I talk about this, it means I have to describe the IKNP protocol again, and maybe I know that I had to see it many, many times before I really believed. So maybe this will help you really internalize what's going on. So let me describe the IKNP protocol. The IKNP protocol says you're supposed to take your choice bit, so Bob's choice bit, and fill up a matrix where every row is either all ones or all zeros. And then you make secret shares of that matrix. So I'm going to consider what happens if Bob is cheating. He's not following the protocol and he just does something different. So in this case, he's just going to flip one bit. I've highlighted the bit here, right? He's supposed to have a row of either all zeros or all ones, but he's cheating. Now he has a row with a single one. This turns out to be a really bad attack on IKNP, surprisingly. So let's figure out what happens. So we take this matrix and we secret share it. So here's the secret shares, and I've highlighted the thing that's wrong. So these two rows are supposed to be either all the same or they're supposed to be complements of each other. But in this case, they're mostly the same except for this highlighted bit, which is incorrect. Okay, so what happens next in IKNP? We go across the columns of this matrix, and for each column, we perform oblivious transfer. So here, Alice has choice bit 0, so she picks up this column. Now she has choice bit 1, so she picks up this column. And I designed it so that she picks up the problematic bit here. Okay, everything else is the same as the previous slides. let's just trace through where this this flipped bit, where it happens. Okay. So when everything was correct, we looked at these two rows and we said that, oh, Alice and Bob actually have the same value in this row. But that's not true anymore, because now Alice and Bob's inputs, they are different in 1 bit. They're different in 1 bit. And actually, if you think about it, suppose they're different in 1 bit because Alice had her S, she had S equals 1 in this case. If she had S equals 0 in this case, then she would have picked up these bits and she would have had a 0 here. So actually, Bob has arranged so that Alice and Bob have strings that are different in 1 bit, and that difference happens if and only if the second bit of S is a 1. Okay, this turns out to be a bad idea. Bad for Alice, but good for Bob if he's trying to cheat. So if you think about it from Bob's perspective, he knows that Alice will either have this this string, a matching string, or she will have a string that's different in the second position, right? If he can figure out which one Alice has, then he will learn this bit of S, okay? So if Alice uses, the protocol says that Alice should take, Alice should compute a hash of this value, and that's her OT output. Well, usually in oblivious transfer, the parties take their OT outputs and they, use them for something. So if Alice uses her OT output in some larger protocol and Bob sees it, well, he can just check, is it hash of my matching value, or is it hash of this other value where the bit is flipped? And based on which it is, now he's learned this orange bit of Alice's secret S. Right, so somehow when Alice uses this, somehow Bob cheated in one place corresponding to the second base OT, and that caused Alice to leak the second bit of her S value. So Bob knows the second bit of S. But of course he can cheat, if there's a million different OT instances, he can cheat in 128 different ones. So in each OT instance, he cheats in a different column. Maybe he cheats down the diagonal. And that means he learns all the bits of S, and he can learn them one at a time. So that's bad. Once Bob learns all of S, well, that was the only secret in this whole protocol. That was Alice's only secret, is this choice of S. And if he learns that, now he knows, he completely breaks the OT extension protocol. So I tried to describe all of these things in terms of these pictures so you can see what's going on, but also I think in terms of the algebra, like this master relationship between Alice and Bob's values, I think it's good to see it in terms of that too. So in IK and P, Alice learns these Q strings. Those are the rows of Alice's matrix. And Bob learns all these T values. And he also chose some secret shares of a matrix. So what I mean is, in this attack, his inputs were like secret shares of this matrix. They're supposed to be all zeros. The rows are supposed to be all zeros or all ones. But when he cheats, he can secret share any matrix that he wants. Okay. So now if we work through what happens here, the relationship between Alice's Q and Bob's T is like this. So Alice's Qi is equal to Bob's Ti XOR the ith row of R bitwise and with S. Okay. And just to double check that this makes sense. So honest Bob, when Bob is honest, the ith row of this matrix is either all zeros or all ones. So when it's all zeros, then you have 0 and S, and this term goes away. So you just get Ti. And when Ri is all ones, well, string of all ones and with S is just S itself, and you get this result. Okay. But in the attack, Ri was a string with just a single one. And a string with just a single one means that this value, you only have to guess one bit of S in order to guess this value. Right here, when Ri is all ones, Bob would have to guess every bit of S in order to guess the value. But if Ri is just a single one, then he only has to guess that bit of S in order to guess this Qi value. So somehow it's problematic that if these Ri values have low Hamming weight. That's something that we'll come back to, I hope, when we have time. So if we want to make this protocol secure against a malicious Bob, we need to make sure that that Bob chooses these Ri values to be always all zeros or all ones. That's the main attack. We also have to consider a malicious Alice, but that case is much easier, so I won't really talk about it. This is the hard case. Okay, so I'm going to show you this consistency check idea from this paper by Keller, Orsini, and Scholl, I think from Crypto 2015. So here is the master equation for IK and P. The idea is that, yeah, here's the intuition. So this equation holds for every row, and actually these equations are additively homomorphic. Like if you add up these equations for many different rows, then because it's the same S here, then all of the things distribute correctly. Like all of these equations, they work nicely together, and you get this expression here. So Alice is going to challenge Bob to a random subset and say, please prove that you've used valid Ri values on this random subset. And so Bob can compute this term, the sum of all the Ti's, and he can compute the sum of all the Ri's. He can announce those. Alice can compute the sum of all the Qi's, and Alice knows S, so she can check whether this condition is true. Okay. And it's also true that if Bob was playing honestly, then all of these Ri values are either all zeros and all ones, and then their sum is also all zeros and all ones. So Alice is going to check this equation, and she's also going to check that this R star value, which is this term, she's going to check that it's all zeros and all ones. Okay, so the nice thing is that this IK and P equation that I have in the box, it has this homomorphic property. It means that we can check, it's like we're checking this condition, but like in a batch of many things by using a linear combination of these equations. So I won't go through the details, but if Bob has any R value that's wrong, so Alice is going to check an equation that looks like this, and she's going to check it with an R value that is all zeros or all ones, but that's not what Bob really used. So he's lying. And it turns out that if he's lying anywhere, then he gets caught with probability 1/2 because he has to guess at least one bit of S in order to give the right answers here, basically. So the protocol that I drew up here, where Alice sends a challenge and Bob sends a response, that catches a cheater with probability 1/2. So just repeat that check many times, maybe 128 times, and Bob has to pass all of these checks. There's one other issue though, is that this secret matrix R is like Bob's OT input. It's his choice bits in the extended OTs. And actually we're leaking one bit of information. We're leaking one bit of information about this R matrix, right? We're leaking like a random linear combination of some of these values. So in order to hide that information, all we have to do is just add another 128 random rows to this tall matrix. So the matrix used to be 1 million rows. Now it's 1 million plus 128. And those are just random values that are used to make sure that this R star value doesn't leak any information about the real rows of the matrix. But that's basically about it. So all you have to do is run this IKNP protocol, and you just have to check many linear combinations of these values, and that will prove that Bob must have used all these correct RI values. So really, there's not much overhead to get malicious security, and this is a trick that I've always thought was pretty nice. Usually in secure computation, you have to spend a lot of extra effort to get malicious security, but in this case, there's almost no overhead to get malicious security. Okay, so the last thing I want to talk about for OT extension is some generalizations. So what I've talked about so far is 1 out of 2 OT. So that means Alice has 2 strings and Bob chooses one of them. Sometimes it's helpful to have 1 out of n OT, maybe 1 out of 8, maybe 1 out of a million. And you can generalize this IKNP protocol in a very nice way. So I'm going to talk about that next. So there's a way to think about the IKNP protocol in terms of error correcting codes, which I think is interesting. And this perspective on IKNP is due to Kolesnikov and Kumarasan. This is a Crypto 2013 paper. So once again, let's look at the IKNP protocol. Bob has his choice bits for every OT instance. The protocol says he should extend these choice bits into a matrix. So every row is either all ones or all zeros. And then he should secret share that matrix. So this is the same picture from every slide today, the same picture. So this paper by Kolesnikov and Kumarasan, it says you should think of this matrix. So there's a matrix where all the rows are either all zeros or all ones. And it says you should think of this as a error correcting code. This is the simplest possible error correcting code. It's just a repetition code. Right, the simplest error correcting code with the 1 data bit and 128 code word length. And it says, if you think of these values as an error correcting code, then what happens if we use a different error correcting code? So this is a trick that I find to be really insightful. Like if you ever see something where the same value is being repeated over and over again, maybe the right thing to do is think about that as a repetition code And usually a repetition code is not the best code for a given problem. There's probably a better error correcting code. And so you can try to think about what happens when you substitute the repetition code with a better, more sophisticated error correcting code. So that's what we're going to do. So here is the generalization, it's not a general. Hi, yes.
First question.
Oh, sure. Yeah, go ahead. Oh, in the Q&A. Okay. I was too sure when Bob sends T star SR star, he could not set T star maliciously. Yeah, good. So let's go back to that picture. Yeah, it's true. So when I said that if any RI is not correct or not valid, then Bob gets caught cheating. Yeah, even if Bob lies about this T star, yeah, so this analysis, I haven't gone into the details of the analysis because you have to work a little bit. But the analysis does say even if Bob lies about T star, so if he lies about R star, then even if he lies about T star, he cannot win. And the important thing, yeah, I'm trying to think of how I can convince you that this is true, but the important part is this term. So if he says the wrong thing about this term, then it's true he might be able to compensate for it in this other term, but he doesn't know how to compensate unless he guesses one of the bits of S, basically, right? So this is saying he gets caught with probability 1/2. So if he lies about this value and he guesses the right bit of S, then he can definitely lie about T star and get everything to work. But the point is that it's necessary to guess one of the bits of S, but S is secret. So so he actually cannot guess all the time. So this is not a perfect check, it's a probabilistic check. And that's why it needs to be repeated several times. So thanks for that question. I hope that answers the question. I've also gotten some notifications that people have hands up. I don't know how to deal with that. But there's another question here. Why we start from 128 basic OTs? What if we start from 2? Is it related to security? Yeah, that's a good question. So yeah, that's actually a great question. So why do we use 128 OTs? I'm sorry, I have to reverse through a lot of slides here. Okay, so the reason we have to, yeah. Let's imagine that we have only 2 base OTs instead of 128. So all of these strings, like these T's, the TI strings, QI, and S, they're all strings of length 2. But in the random oracle model, yeah, random oracle applied to strings of length 2 is never really pseudo-random, right? The problem is that Bob could guess this value S. If S is a string of length 2, Bob can guess it, and then he can recognize these strings. Or in other words, oblivious transfer says that these values that Bob doesn't learn, they must look random to him. So in order for these to look random, he can never query the random oracle on these values. And that means that it should never be possible for him to guess the value S. That means S has to be a large enough string that it's impossible to guess in polynomial time. So that's why S has to be 128 bits. I think we'll see we'll see more details about that in the next section. I just want to keep checking the Q&A. Answer live, answer live. Thanks for those questions. I'll try to keep I'll keep this Q&A window open. So if you have more, oh, but it doesn't stay on top. Sorry, the Q&A window, which you probably see covering my screen, it doesn't want to stay on top. So I'll have to keep checking that. But yeah, please use the Q&A feature for your questions. Okay, let's get back to this. Oh, I went too far. Okay, so we're talking about this error correcting code view of the IKMP protocol. Bob is supposed to take secret shares of a matrix where every row is a repetition code of his choice bit. So let's just write the IKMP protocol in terms of that perspective. So he has these choice bits. He encodes them under an error correcting code. So for now, that code is the repetition code. So now he has a long matrix where every row of the matrix is a code word. He secret shares that matrix. And then they do the base OTs, and that's all the usual thing here. Now, if we look at this master IKMP equation, which relates Alice's view to Bob's view, it looks like this. So TI and QI are different, and they're different based on the code word in that row, bitwise and with S, right? And I think this follows from what was in the previous section, right? In the ith row, these two matrices are secret shares of the code word C of Ri, right? And so then that's the thing that gets logically bitwise and with S. Okay, and again, if this is confusing, just go back to a repetition code, right? If the only possible code words there are all zeros or all ones, right? And so we get the values that we're expecting there. Okay, so if we keep going through the rest of IKNP, we can say that Alice and Bob start out with these Q's and T's. Alice should compute this weird looking thing. So QI XOR code word of 0 and S, and here code word of 1 and S. Those are two things that she can compute. And Bob's value is one of them. Right, so here I have these Q's. This is what Alice does. And now instead of thinking it in terms of Q's, I want to think about it in terms of the T's from Bob's perspective. So I replace every Q with a corresponding T using this equation, and I get this ugly looking expression. But if this code is a linear code, then actually, these logical ands with they distribute nicely across a linear function, and you actually get a simplification here. So I simplified it in this way. And when C is a linear code, C of 0 is the all zeros code word. And so those terms go away. So here, I'll just highlight, here's one place where this was C of 0. It was the code word C of 0. That's all zeros. So this entire term disappears. And you get this picture again. This is just a repeat of the original IKNP because, this C of 1 just means all ones. And so everything makes sense. And then you do a random oracle of those values. So this is just the same as IKNP, but just looking at it from error correcting codes. So what if we used a code? The repetition code is just for a single input bit. What if we use an error correcting code for 3 bits, just as an example? So now C is a linear error correcting code with 3 data bits and k code word length. So now there are 8 different code words. So Alice can compute 8 different values like this, right? 8 different values that Alice can compute. If we look at those 8 values from Bob's perspective, they look like this. By the way, now Bob's choices, these RI values, they're no longer bits, but each of them is a 3-bit long choice. So from Bob's perspective, these 8 values look like this, and exactly one of them will be known to Bob, right? What if R1 equals 111? Then this whole term goes away because this is a code word of 0. And so that means that T1 is actually this specific value. So now we have a situation where Alice knows 8 things. In each row, Alice knows 8 things. Bob knows one of them. And the things that he doesn't know have this property. They're T XOR some code word, like some non-zero code word, bitwise and S. And if we have a code where all of the non-zero code words have high Hamming weight, then this is actually secure. So I want to argue that, suppose Bob learns this value, then all of the other values from his perspective, they look like this, whereas C1 is a non-zero code word. So imagine if C1 has Hamming weight 128, then Bob would need to guess 128 different bits of S in order to guess what this logical AND term is, right? So this is another reason why, like, there's something special about requiring Bob to guess so many bits of S. Yeah, so basically what we're looking for is, yeah, when I'm saying that all non-zero code words have Hamming weight equal to 128, that's just saying I want a code with minimum distance at least 128. Of course, now we might need more than 128 base OTs, but for yeah, so this is the main result of this Kolesnikov-Kumarasan. You use a code. So I'm trying to connect the parameters of the code to this OT extension. So if you take a code that has L data bits, then you get a 1 out of 2 to the L OT extension, right? Because there's 2 to the L different code words. So in this picture, Alice will compute 2 to the L different values, and Bob will know one of them. If the length of the code words is K, then you need K base OTs, because you have a matrix now with rows of length K, and you do base OTs for every column of that matrix. And you just need the minimum distance, you need the minimum distance of the code to be equal to the security parameter, or at least the security parameter, right? And that's what makes it secure, I guess. So that's what causes all of the other values that Alice knows, they look random from Bob's perspective if you have this minimum distance requirement. So in their paper, they suggested, hey, you can use a Walsh-Hadamard code. So using 256 base OTs, you can do 1 out of 256 OT. This other paper by Oru, Orsini, and Scholl, they went crazy. They said take a BCH code, with 76 data bits, then you can do 1 out of 2 to the 76 OT, which is basically like 1 out of anything, using 512 base OTs. That's how long the code words are. Myself and co-authors, one thing we realized is that you don't need, the only property you need of these code words is sorry about these slides jumping around. the only property that you need about these code words is that they have high Hamming weight. You don't actually need error correction, right? We never run the decoding algorithm of the error correcting code. So it turns out that you could just use a pseudo random function as instead of a linear code. Yeah, in fact, you can get around using, the way I described it made it sound like you need a linear error correcting code, but you can survive even if it's not a linear code. So we showed that you just need a pseudo random function with about less than 500 input bits, and now you can encode, right? So the size of the input to the code gives you like the size of the 1 out of n OT gives you the n. But here you can have it's not really a code, but you have an object that has an unbounded input length. So that means you can get like 1 out of infinity OT. That was one of the things we called it. So basically, for every string in the world, Alice can compute a secret, and Bob gets to learn one of those secrets that he chooses. So that's a useful function in some applications. All right, so this is, I think, my last slide. The lesson is that oblivious transfer does not have to be expensive. It can actually be very cheap. So one of my former PhD students has implemented a lot of these OT extension protocols, and they're extremely fast, right? So 20 million instances of oblivious transfer per second using these OT protocols. So yeah, hopefully today I convinced you that oblivious transfer, even though it's expensive, you can't get oblivious transfer from symmetric key techniques. You can still get millions of oblivious transfers from just a small amount of public key operations, just enough to do the base OTs. OTs are cheap. All right, I think I'm done. That's my last slide. So I'm happy to take questions as usual. And I see that there are some in the Q&A. I don't know how to sorry about this. I'm trying to put this off to the side. So how can, I did answer that. I did answer that. Okay. Does this 1 out of 2 to the n OT still resist Bob's malicious attack? Yes, good question. Yeah, so I showed this generalization, 1 out of 2 to the n OT. And yeah, this is a great question. So I just showed how to generalize I, K, and P. I didn't show how to generalize this consistency check from Keller, Orsini, and Scholl. Now let's look at this slide from our coding perspective. So here, if every row Ri is a code word and it's a linear code, then the sum of all of the code words is also a code word, right? That's all this thing says. I don't know why it won't let me select. Yeah, but yeah, if you reinterpret this line in terms of error correcting codes, for linear error correcting codes, this is just the definition of linear, right? The XOR of a bunch of code words is still a code word. So Alice will do the same thing. She will check that this R star is a valid code word. And if Bob has any row where he doesn't have a valid code word, then he will be caught with probability 1/2. And so all of this stuff still works, even though I didn't really describe that part in this generalization. The consistency check still does work. So this paper, Oru, Orsini, and Scholl, they actually they show a semi-honest and a malicious protocol. So they generalize this consistency check from the 1 out of 2 case. They generalize it to their case as well. But this protocol, where we replace the error correcting code with just a random function, that was enough for the semi-honest. But because this thing was not linear, this protocol is not secure against malicious parties. So that's kind of an interesting situation. So you need a linear code to do malicious security, to do this check, but you don't need the linear code just to do semi-honest. And you can do better by doing something that's non-linear. So thanks. That's a great question. Answer live. Could you give a brief intro to ECC version ICANN? Oh, okay. So yeah, I think that was the same question that was on everybody's mind. Is it possible to reduce the communication complexity of OT extension? It is possible. So in the last few years, there's a line of work that's very recent, and it's called silent OT. And it uses a completely different method. And I don't have slides for that because it's all very new within the last maybe 1 or 2 years. So the communication costs for silent OT, so it's just a different approach to OT extension. One thing I didn't say was how much communication is involved here, but basically if you do 1 million OTs using this technique, you need to send about 1 million times 128 bits. So it's like 128 bits per extended OT. This silent OT, I mean, I don't know all the statistics, but you can do each OT for just maybe 5 bits, 10 bits, but you need to generate a huge number of OTs before you get the communication that small. Like, I usually talk about millions of OTs. In their paper, it's maybe tens of millions or hundreds of millions of OTs before you get them that small, right? So in an amortized sense, they can get the communication much smaller. But if you still want maybe just a few million, then I think IKMP is still the most efficient. Although I'm not so sure. There's been a lot of papers about this in the last year, and I don't remember exactly where the cutoff is. So there's this other silent OT technique. It has a lot of fixed costs. So think of it as a lot of costs, kind of like for the base OTs, much larger than IKNP. But after that fixed cost, the things become much cheaper for each of the extended OTs. Yeah, so if you're interested in that, you can find papers that have silent OT in the title, and there'll be several of those that you can read. Okay, are there any other questions? I think we're reaching the end of our time here. Let me check in the chat. Oh, there's just that's not a question in chat. Yeah, I don't see any other questions. Is someone unmuted that wants to ask a question?
Okay, since there are no more questions, and let us thank Mike again. And it's a really nice talk. And I think there is extra one lecture in the series. When is that? Next week. Okay, so
yes.
Yeah, if people are interested in this series talk, you can just come and Mike will give the last lecture in the next week. Okay.
Yeah, the next week's talk will be about private set intersection, which is a special case of secure computation.
Okay, that's great, and thanks.
There's one final question in the Q&A about what is the fastest base OTs. Actually, my students and I have a paper about the best way to generate base OTs, and we're going to put it on ePrint in the next week, probably. So if you look on ePrint in the next few weeks, we can answer that question. But there's a lot of different protocols. It's hard to pick the best one.
Yeah, if you have any question or if you're interested in the talk, you can just talk with Mike offline.
Yes, please send me an email if you have questions.
Yeah.